Welcome back to this NPTEL online certification course in molecular rearrangement and reactive intermediates. We are talking about the organosulfur chemistry. So previously I talked about the different type of the sulfur reagents, and last classes especially I talk about sulfur based ylides. So if you have missed the class, that is a very important class. We talk about the reactivity of sulfur based ylides. There will be stabilized versus unstabilized. And if you talk about the reactivity to enones, some cases you will find 1,2 addition, some cases you will find a 1,4 addition. One case you will get a epoxide if it is 1,2, and 1,4 will give you a cyclopropene. In the today's class I am going to talk about there are several different oxidation reaction of alcohol which actually use sulfur based reagent, different type of sulfur based reagent. So we are going to discuss them, and mostly they are actually activated DMSO. So let's talk about them. So first I think I talk about this the reaction which I missed in the last class. I talk about some of these things but not in the details. Is the Corey-Czakowski reaction. The Johnson-Corey-Czakowski reaction is a very important one. And after that, the rest of the class I am going to talk about this activated DMSO. So you are going to see that, which I told you in the last class, a very important lesson, that once you think about a DMSO, you should think about the electronegativity difference between sulfur and oxygen. The sulfur having electronegativity of around carbon 2.58 and oxygen is 3.5. So that is why the electron density is actually lying mostly on the top of oxygen. So you can write them very comfortably, S plus and O minus. So these things you are going to see, we are going to use again and again to explain these several different oxidation, the Kornblum oxidation, the Fitzgerald, the Moffat oxidation, the Farik-Doering oxidation, Albright-Goldman, and the Corey-Kim oxidation. So you are going to see in case of Corey-Kim, we are going to see there is some in these cases, in this 4 of them you will see the alkoxysulfonium ion, okay, and here you are going to see you are going to come back to that, some sort of SPC like that. Let us come back to that discussion. Okay. So first thing we talk about the Johnson-Corey-Czakowski reaction. Again, this is a, as you see, this is a name reaction, and Professor E.J. Corey has a lot of contribution to the organic chemistry. This is not only a single reaction, he has done a lot of work, a lot of natural photosynthesis, several different methodology, several name reactions from his name, and he was awarded in Nobel Prize in chemistry in 1990. So here I am going to talk about a reaction. I think I already talked about that when I talk about the stabilized and unstabilized one. As I did not have much time, so I only talk about the name of the reaction, but here I am introducing you that this reaction, once you have this ylite and you attack to the corresponding aldehyde, you will be able to generate epoxide. But the important thing to understand, regardless of this the geometry, you will end up getting to the trans product, okay, trans epoxide. If you have react with the imine, you end up getting trans aziridine. And if you have a if you have alpha beta unsaturated carbon compounds, then you end up getting a cyclopropane. Again, you can see these are these again these are trans. Okay. So we are going to understand why in every cases they are forming this trans product. We are going to learn about that. What is happening here? Once this corresponding carbon ion, okay, which is forming here, going to attack, okay. So when it is attacking to the corresponding carbonyl group, then you can understand we are forming 2 chiral center here, correct. So now you can think about that when this nucleophilic attacking happens. I think very similar discussion we have done with the Peterson olefination, that when it is forming this silanol, when the attacking happening to the carbonyl group, here we have sulfur instead of the silicon. But the similar problem arises that when this nucleophilic attack is happening, the important thing is that the corresponding geometry of this particular compound which is forming this, it will be anti-betaine intermediate or a syn-betaine intermediate. So once this attacking is happening, there is this sulfur R2 and the R1, and there is R2 here in the aldehyde. So once the attacking is happening, to avoid the steric class, the R1 and R2 try to be as far as possible, okay. So if that is the case, then the anti-betaine will be more favorable compared to the syn. You can see here in this particular conformation, you have X minus R1 Gauss and then R2, R1 R2 Gauss and then R2 SR2 Gauss interaction. But here you can see there is only 2 Gauss interaction between these two. Okay, and also this R1 and R2 actually anti. So because whatever the you can see about if he is coming back to this or always to the to the anti, then at the end you will be able to form the corresponding trans product. If it is epoxide or if it is aziridine, doesn't matter, you end up getting to the corresponding trans product. And again in case of the cyclopropane also, when you are going for the attacking here, again the orientation of these groups are very important, so that this this R3 and R1 again they will be try to prefer in the corresponding tangent state trans to each other, that will end up giving the product which are also trans. Okay. Now we are talking about this reaction here. You have this the elite which is from the the sulfoxynium. So that can, if you have this scenario here, there is a possibility attacking here, but it is conjugated, so it will be attacking in this position, because one of the reason is you can see this is already a tri-substituted one and this is a terminal position, so the CH2 minus will prefer to attack here. Once it is going to attack here, it is going to form the corresponding O minus, correct, which is going to come back and going to form the corresponding cyclopropane. Okay. So if you try to draw that, let's try to draw it. Maybe if you not able to pick it up. So you can see this is the scenario here. Okay. So now this is going to come back and this is going to get rid of this the methyl here to form this corresponding cyclopropane. Okay. Now if you have this in the alpha beta unsaturated compound or alpha beta unsaturated carbonyl compound, again this is going to go for a 1,4 addition here, it is going to attack here and going to form a corresponding cyclopropane here. Another scenario here, this is another alpha beta unsaturated carbonyl compounds, so this will go for a 1,4 addition to form this corresponding cyclopropane. It can be it can also go do this the homologation of epoxide and aziridine. So what is going to happen? Sulfur halides can be used to homologation of epoxide and aziridine to form the corresponding oxatane or azitidine. Okay. So the aziridine is going to convert to corresponding azitidine. You can see there is a homologation happening. You see you are introducing one carbon here. So this is the carbon getting introduced, which is coming from this CH2 minus. Okay. So again you can see if you use a potassium tarbate oxide, that can be able to generate this compound here, which can be generated in situ, and now it can attack to the terminal position to open up the epoxide, and now this O minus can attack to the corresponding the CH2 to get rid of the SO2Me to get to the corresponding the oxatine compound. So these are the oxytane compound and these are the azitidine. You can see the mechanism is already given here. First the ring opening by attacking to the terminal position, and then this minus can attack to form this corresponding azitidine or corresponding oxytane. Okay, there are enantioselective selective variants was developed by Agarwal group where they can able to generate this starting from this chiral. Now you can see we previously talked about sulfur with 2 methyl, correct. So we talked about previously sulfur with methyl and generation of CH2 minus, but here we are talking about that there is a chirality, there is a this compound is a chiral compound, and not only that, there is another important factor here. Because of this if you try to orient in this particular conformation, then this R group and H group will have a steady, so it will try to, so there will be equilibrium between, once you try to generate this corresponding the corresponding the carbon ion, and it is going to prefer to react in this particular tangent state will be less energetic compared to this one. So you can able to control the attacking of this CH2 minus this corresponding carbon ion to the particular phase of the carbonyl group. because of this steric interaction between this group to this R group, okay, and also the first most important thing is this equilibrium. So this equilibrium will always going to favor to this side, okay. So once this is the measure in the solution, so this is going to react with the corresponding carbonyl compound. Now it is going to attack to the carbonyl compound to a particular phase. Now it is able to control the enantiomer selectivity of the epoxide, okay. See, using a stoichiometric amount of chiral compound, you can able to now control the enantiomer selectivity of the epoxide. So from using this camphor derived chiral auxiliary. So you can see this particular chemistry, as I mentioned, that if you generate this, so this will be a more reactive unstabilized carbon, unstabilized halide. So from the sulfonium that can react with the carbonyl group to generate epoxide, which can be used for the synthesis of Taxol. It's a very important anti-cancer agent. And then there is the synthesis of strychnine here. Here also you can see that first thing is from this aldehyde, once you form this corresponding epoxide, correct, using this again using this unstable halide, it is going to form this corresponding epoxide, and then this nitrogen can open up the epoxide, and at the end it can be, after few steps, it will be converted to the strychnine. So I already talked about some of the things which I already mentioned here, that converting the corresponding carbonyl to epoxide, or if you have alpha beta unsaturated carbonyl compound, you can generate the cyclopropane. Okay. Now I am going to moving further and talk about some of the oxidation reaction where you are using the activated DMSO. Okay. So here we can see that using this activation DMSO and triethylamine, the first one is the Korn-Blum oxidation. So this is a conversion of primary or secondary alkyl halide or tosylate into carbonyl compounds using a base and DMSO. So what you are doing, you are converting a corresponding primary or secondary corresponding alkyl halide. So this could be X, this X could be a, so you see this is alpha halocarbonyl compound. If you have this corresponding alpha halocarbonyl compound, it could be a primary or secondary, you use DMSO or triethylamine, okay. This here you can see this R2 could be could be a alkyl, so R1 R2 could be alkyl or aryl, okay, and the X could be a chlorine, bromine, iodine or tosylate, okay. The OTS is very famous for this reaction, but alkyl iodide and the tosylates are very much used. Also if you use the bromide, then you have to use the silver BF4 or silver OTS for this reaction. But the reactivity is the tosylate and iodide will be faster compared to the bromide and the chloride. The base playing a very important role here. We are going to come back to the mechanism, and we are going to see the base has a very important role, because as you are using this the iodide or bromide, you are going to generate the HI or HBr that has to neutralize, okay. So that is actually this is going to facilitate the deprotonation, at the same time it is going to neutralize the HX which is going to form in the reaction. So here what you are seeing here, from starting from this alpha halocarbonyl compound, you are forming this 1,2 dicarbonyl compound. So you can see these are 1,2 dicarbonyl compounds. Or you starting from the corresponding benzylic halide, also this reaction can be work, you can generate corresponding aldehyde. So literally from a benzyl bromide or benzyl iodide, you can convert to corresponding benzaldehyde using DMSO and triethylamine. So such a simple reagent. So there is some sort of a modification here, as I mentioned, that if your X equal to if your X equal to halide, first thing you want to do, you want to convert to corresponding OTS. So if your X equal to bromide or chloride, then first thing you have to convert them to OTS, okay, then only the reaction can be done. That means the reaction mostly done by OTS or iodo. If you have a bromide, then you convert them to OTS, which can now participate in presence of DMSO and to get to the corresponding aldehyde or ketone. Okay, or you can use this silver BF4, which can also allow you to the reaction to happen. So let's try to understand in this reaction. Again, I think whatever, if you use silver or the OTS, what you are trying to form, you are trying to act as a leaving group, or in case of silver, you are trying to form some sort of a carbocationic character. So that means if you do that, if you in this reaction, the most important thing, if this is a very very good leaving group, then this O minus from this, the DMSO can attack here to get rid of the X through SN2 reaction to generate this alkoxy sulfonium ion intermediate. Okay. Once you have that, now you can use this triethylamine. Triethylamine can able to, because the methyl group next to the sulfur, so can allow this deprotonation. This is the important role of the triethylamine, can generate this CH2 minus, which can able to take this proton here, form this double bond between carbon and oxygen, get rid of the sulfur, okay, to get to this 1,2 dicarbonyl compound. Or if you have a silver OTS, then you can form this corresponding tosylate. Here again, once you have the tosylate, then the sulfur, the O minus is going to attack here, get rid of the OTS. You are generating this again, this alkoxy sulfonium. Once you have the alkoxy sulfonium, now you have this carbonate here, and you have the base which can able to get this corresponding carbon ion, which can able to take this proton, form this carbon oxygen double bond and get rid of DMS, the dimethyl sulfide, to get to the corresponding carbonyl compound or aldehyde. So you can see some of the application of the Kornblum oxidation here. They are trying to synthesize this fluorescent nucleotide. In this synthesis, you can see from the starting material to the product, there is a NH2 here at the beginning. Now you are seeing here, this is forming a imidazole. Okay, so you can see there is already a 2 nitrogen. We can see clearly this is the nitrogen and this is the NH2 nitrogen, but this rest of the part actually came from this part. So you started from this COCH2Br. So if you start with COCH2Br, if you remember, using DMSO and DBU as a base, in situ they are forming a glyoxal. That means what is happening? You are in situ generating this species after this Kornblum oxidation. COH. So once you are generating this glyoxal, now what is happening? You can see there is NH2 and there is AN, that's going to do a condensation to get to this corresponding imidazole. Other example here, again you are using DMSO and sodium bicarbonate. This again benzylic bromide converted to corresponding benzaldehyde, which can able to introduce to the to further convert to the analogues of anthraline, okay, by converting this corresponding aldehyde to the cyano. The Fitzner-Moffett oxidation. Okay, it's an oxidation of primary and secondary alcohol. So we, of course, you guys have learned about the chromium based oxidizing agent, correct? The PCC, PDC. But there are, of course, you have heard that sometimes this type of reagent has some sort of limitation. Okay, sometimes you need those type of chromium. Of course, the first thing that the toxicity has a huge problem, but there are also several other limitations for those reactions. So here I think the sulfur based reagents are very good alternative for that. So this was discovered in 1963 by Moffett and Fitzner. So it's a mild reaction condition, and most important thing, most functional groups are tolerated. The reactions don't have like a very strong base or don't have a very strong acidic condition, which you must have seen some sort of chromium based oxidizing agent. So here using just simple DCC, which is a neutral reagent, and using DMSO with a catalytic amount of acid. Okay, it could be the pyridine HCl or pyridine TFA or the H3PO4. Using a catalytic amount of acid, you can able to convert the corresponding primary or secondary alcohol to the corresponding carbonyl group. So not only the DMSO is always used as a solvent, sometimes you can use a inert co-solvent like ethyl acetate or benzene in this reaction. Okay, so that can make the isolation easier, because if you use only DMSO, because of the high boiling point, sometimes it will be difficult to remove. So we talk about the Fitzner-Moffett oxidation. Now we are going to move further and trying to show you the mechanism of this reaction. First thing is one of the important thing of why you need the acid. You have to activate the DCC here. So DCC, you can see these carbon nitrogen bonds are there, these imine bonds are getting protonated. Now this carbon is getting attacked by this DMSO oxygen. Once you are forming this alkoxy sulfonium ion intermediate, once that is formation is happening, now this sulfur is getting hit by the corresponding alcohol. The alcohol oxygen is attacking on the sulfur, formation of this species here. From here what is happening, you can see this nitrogen can able to, you can think about that, like once you have this species, then this can take this proton, minus formation happening, this can generate this corresponding CH2 minus, correct. And once it is forming the corresponding CH2 minus, you have this alkoxysulfonium elite, correct. Once you have this alkoxysulfur, because you can think about this CH2 minus, or you can write like that also, that it will get rid of this part going to get rid of and forming a urea here, dicyclohexyl urea, and you have this CH2 minus, or you can write them as elite. This is alkoxysulfonium elite formation happening. Once this elite, you know that next thing is very easy, it can take this proton, form this double bond carbon oxygen and get rid of this. So as long as you are generating this alkoxysulfonium elite, you can able to get to the corresponding product very easily. So from there, this can able to as I mentioned, going to get to the it can form the dimethyl sulfide and the corresponding carbonyl compound. Here there is an example, you can able to convert this to the, so if you have this diol, you don't have to use a PCC, you can use this condition to comfortably get to this 1,2 dicarbonyl compound. Okay. And the important thing is, as there is no other acid or in much, there is some sort of pyridine TFA, but again this type of reaction condition is better than the chromium based oxidation, because sometimes chromium based oxidation can also allow the diol cleavage. Okay, that is also another important factor. So if you use chromium based reagent, there is a possibility of diol cleavage, that's why you might get a poor yield in this reaction. Okay, then there is, in this particular reaction, you can see there is a very sensitive functional group there here. Okay, if you have sensitive functional group, then this condition is much better, giving you this corresponding, you are forming the corresponding aldehyde in a very good yield. If you use DCC or the Des-Martin periodate, what is going to happen? This reaction has a low yielding. Okay, so that's why this condition is much better. Another synthetic application here, again you can see this is the primary alcohol, and there which can be comfortably convert to the corresponding aldehyde here, and then you can use them further. You can using TBAF. If you remember, we talk about this the F minus as a deprotection of the corresponding silicon, so that can generate this O minus, which can attach to the aldehyde to get to this natural product. But again, I think one of the problem is that in this reaction the DCC have a problem. So again, I think this is a very common problem, that once this urea going to form, it was difficult to remove, correct. So that's why I think in the amide coupling also this was a problem. That's why EDC was introduced, which can be water soluble. I think the EDC can be used because the urea which is going to form, that is water soluble. Okay, so correct me. So the EDC going to form the urea which is water soluble. So that's why EDC is better compared to use of DCC in this reaction. Then the pairing during oxidation, here what is happening, again this is oxidation of primary or the secondary alcohol to the corresponding aldehyde or ketone. It was so the reagent here is SO3 pyridine and DMSO, and triethylamine or some sort of a base you need to use. So DMSO act as an oxidant as well as the solvent here. Again, you can see both the cases, DMSO can as an oxidant as well as a solvent. Every cases, sometimes DCM is frequently used as a co-solvent. Okay, so and then this reaction can be done at 0 degrees to the room temperature. You don't have to go to a low temperature. And this can also convert allylic alcohol to the alpha beta unsaturated carbonyl compounds. Mechanistically, again you can see this is the activated DMSO going to attack to the SO3 pyridine to form this compound. Again from there, what is going to happen? You are generating some sort of alkoxy species here, alkoxysulfonium. Now you have the pyridine base, but you have the alcohol which can attack to the sulfur, which have a positive charge there. Once you have this alkoxysulfonium species here, that can able to if you have a triethylamine or you have a base in the medium, that can generate this corresponding elite, which can able to abstract this proton, form the carbon oxygen double bond, get rid of this dimethyl sulfide. So the mechanism are very similar, you are just changing different species here. Okay, the oxidation of primary alcohol can be done acetic anhydride and DMSO. Again, very simple condition that will introduce you to the Albright Goldman oxidation. So acetic anhydride and DMSO, sometimes this reaction are done at 4 degrees Celsius. you can able to convert the 1 degree 2 degree alcohol to the corresponding aldehyde or ketone. Okay, this was discovered by Albert and Goldman in 1965. This can also useful for the reaction using sterically hydral hydroxy group, can be easily oxidized. Okay, and also this reaction after the oxidation primary alcohol, this reaction end up to the aldehyde, not goes to the corresponding acid, which you see from some of the chromium based oxidizing agent. Again here the mechanism is very similar to, you can see this is a activated DMSO species attacking to the acetic anhydride to get to the acetyl group. So now again it will going to take you to the generation of some sort of alkoxysulfonium ion intermediate going to form. Now this O minus going to come back and this is going to get out as acetic acid and then you have this S plus, so alcohol oxygen going to attack here. From there again there will be this ACO minus going to take this proton to generate acetic acid, as I mentioned, that can form a get out as acetic acid. And what is going to happen, the acetic acid also present here. Now this is going to take a proton from the alcohol and this is going to form the double bond here and get rid of the, so you are seeing here it is going to get rid of, so two things is happening. One is dimethyl sulfide is getting out here, also it is generating another acetate here. Okay, so one acetate is getting out, one acetic acid is forming and it is going back to the corresponding carbonyl compound. Okay, so first thing is attacking here, I think you understand that, then it is coming back, so you are getting some sort of acetyl here and now the alcohol is attacking the sulfur, that is the, once the sulfur is positive the alcohol is attacking the sulfur, then this this ACO minus coming back, formation of acetic acid, then another ACO minus attacking here to form the corresponding carbonyl compound. There are some, so this has been commonly used in the large scale synthesis and in the carbohydrate chemistry. Again these are very easy reaction condition, so that's why once you have a carbohydrate chemistry, when you have a sensitive functional group like other alcohol unprotected group, you don't want any acid in the reaction medium. So that's why this is a very mild condition and going to use for conversion of this OH to the corresponding carbonyl group. Here also you can see you have this ester group here, so there are a lot of different functional groups are tolerated. This alcohol can be converted to the corresponding carbonyl group here. So the final, I think we already talked about the activated DMSO. The final one is here is the Core-Kim oxidation. Again we are generating some sort of a species here, but not using a DMSO. So again I think one of the problem using DMSO is that if you have a DMSO is a high boiling compound, so getting rid of DMSO from the reaction mixture was a challenge. That's why if reaction can be developed without DMSO, then that will be useful. So the Core developed this reaction called Core-Kim oxidation. Here they use N-chlorosuccinamide and dimethyl sulfide. So together of these they are going to generate this. You need to, first of all, this sulfur with a positive, correct? But instead of oxygen there is a chlorine here. So this is going to now act as an oxidizing agent. We are going to come back. So reaction is particularly application in 1,2-diol, in which one alcohol is tertiary to give a alpha hydroxyaldehyde or ketone without rupture of the carbon-carbon double bond. Again if you have a diol, then the diol rupturing or is one of the problem that can be easily avoided using this condition. Although allylic and benzylic alcohol cannot be oxidized, they are converted to the corresponding allyl and benzylic chloride under this condition. So you can able to convert them to the corresponding allyl or benzylic chloride. So let's try to understand this reaction. Again you can see you have a tertiary, you have a primary. The primary is getting oxidized without doing any rupturing of this. Mechanism, again you can think this is a electrophilic halogen source, N-chlorosuccinamide. Here this is a nucleophile getting attacked to the chlorine, forming this dimethyl chlorosulfonium ion. So once the dimethyl chlorosulfonium ion formation is happening, this is again sulfur plus, so the alcohol is attacking. So again this N minus is attacking first to form this is called the Core-Kim reagent, and now this oxygen can attack to the sulfur still having the positive charge and forming this species. Again you have a triethylamine that can able to abstract this proton to generate this the corresponding ylide here, the sulfonium ylide. Now once you have this stage, which is the last stage for a lot of this oxidation you have seen, Now this CH2 minus going to take this proton, form the double bond and get rid of dimethyl sulfide as a gas. Some of the synthetic utility here you can see in this particular compound, there are so many protecting group for the alcohol. You can see there are TMS protection there, and you have this this alcohol is selectively getting to the oxidize without any problem, which can convert to a natural product. So you can understand in presence of this silyl protecting group also this method is working very nicely. Another example also here, I think again you can see here it was used for the the synthesis of the cephalotaxin. Sorry, it's called the cephalotaxin. So we can see that this reaction can be used for the synthesis of another important natural product here. Again you can see here you have this 1,2-diol. So these are the important class of compound. Both of them going to convert to the diketone, which can be able to convert to the corresponding natural product. So again, if you have this 1,2-diol, it is oxidation take place without the diol cleavage. That is the very important message here. In this particular part, we talk about the Korey-Czakowski reaction. We talk about some of the variation there. Then we talk about the activated DMSO oxidation here, and then finally we talk about the Korey-Kim, where you use the N-chlorosuccinamide, okay, instead of the DMSO. So you can avoid DMSO using just DCM as a solvent here, which is much better. Again, here are the references for this particular part, and again thank you so much for coming to the class. I am going to see you in the next class. Thank you.